Hey everybody, we are live. Welcome to session 1.0 of the 2024 STEMNetX Coding Bootcamp. I'm your semi-fearless leader, Mike McCracken. I'm a professor here at Washington and Jefferson College. I'm excited to have you in this asynchronous session. The first thing that we're going to do is we're going to talk about how to install our Python distribution, and then I'll show you how to get the workshop notebook files. And then we'll just start plugging away on learning some basic Python syntax. So the first thing that we want to do is I have a screen recording going here. It looks like we're recording. I spent about a half an hour this morning making sure I had no embarrassing browser tabs open. The first thing that we're going to do is I'm just going to get a new tab and do a Google search for Anaconda Python. Just because you don't have that in your search history or your browser history. And the first hit here is exactly what we want. So as will be explained in much greater detail in just a little bit, we're going to be using this large package, large suite of software called Anaconda. Anaconda is a package that's developed and maintained by a company called Continuum. So they do make money off of this packaging of some open source software, but we're not going to pay for it. So if you go to this page, this distribution, anaconda.com/download, you'll want to enter an email address. Make sure you enter a personal email address and not your school email address for reasons that might become clear later. And then go ahead and click submit. So I'll just do this. Let me do this. My email address is in there. I've already agreed to that many times. I'm going to hit submit. So I'm going to accept all. Now I am on a Mac machine and I'm actually using Apple Silicon. So I would click this first option. Many of you are either going to be on an Apple Silicon Mac or maybe an Intel Mac. Some of you will be on Windows machines. That's great. We love Windows machines. There's only one option for you. So you'll click whatever is a good fit for you. If anybody's on a Chromebook, please get in touch with me and we'll talk about how you can access this software in some other way. It's a little bit difficult to install on a Chromebook. It's possible, but there are a lot of hoops to jump through. So you'll go ahead and down this. You'll click the installer. I'm just giving you a thumbs up. I didn't mean to do that. You'll click the installer to run the installer. It'll go through some installation options. Pretty much just click all the standard ones and you should be good to go. Once that has happened, once the installation process has proceeded, you will have a new application on your machine called Anaconda Navigator. Let me get a new Finder window. So Windows people will access this in a different way. I'm just going to go, because I'm on a Mac, I'm going to go to my Applications tab here. Anaconda Navigator is what we want. So as I mentioned a moment ago, and as you'll read more about in a little bit, Anaconda is a huge collection of software. We really only want a few bits of it. Anaconda itself is so big that it actually has this nice little application called Navigator, which gives you like a graphical user interface for selecting which software you want to work with. I'm just going to open this up. If you're on a Windows machine, you should be able to find Anaconda Navigator under the Anaconda package in your Start menu, down in the lower left-hand corner of your screen, or you can probably just search for it. I'm not a Windows expert. I'm sure you know more than I do. All right, so here we are. Anaconda Navigator opened. When I double-clicked that icon, it opened in a different desktop for me, so I just dragged it over here. You can see in Anaconda Navigator, it's giving us a little kind of like data pane. Whoops, what's going on here? Something's wrong. Oops, hold on, I have another dialog box open. All right, there we go. So here's a kind of really high-level set of applications that come packaged in Anaconda. We're going to be working mostly with Jupyter Notebook. Now, when you install Anaconda, Jupyter Notebook should come already installed. I've installed Anaconda in a little bit of a fancy / dumb way, so mine isn't already installed. But you should have one of these blue launch buttons underneath Jupyter Notebook. You can go ahead and click that now, and it'll open up Jupyter Notebook. I'll talk more about what a Jupyter Notebook is in just a minute. Basically, what's going to happen is it's going to open up this new application called Jupyter Notebook. It's going to look just like a browser tab because it is a browser tab. You might need to tell Jupyter which browser you prefer to use. You can use any browser within reason. You're using Chrome, Firefox, Microsoft Edge, I think works fine, or whatever the Microsoft browser is now. So this guy will go ahead and open. Now, as I mentioned a moment ago, I'm going to open Jupyter Notebook in a slightly different way. So everything I'm about to do, you can just go ahead and ignore. Okay, so this is going to pop up as a browser tab. And when you do that, you should see something like this. Now, you will not have all of these files already in this directory, so don't worry about that for right now. Actually, I'm gonna get out of here and go to a slightly different place. Just ignore this again. I'll probably wind up cutting this out of the video. Working directory, because I want to do everything the way that you're doing it. Okay, I'm just going to reopen Jupyter Notebook. All right, when this thing opens up as a browser tab, this is pretty much exactly what you should see. We have no files to select in here. I'll talk about how to get the notebook files in 1 minute. But at this point, if you're able to get here, you've already succeeded. You've climbed halfway up the mountain of Python here. This is a pretty big step. You have it installed on your machine, and you're ready to go. If you get here and it doesn't look like this, or you can't get here, please shoot me an email and we'll figure out some way to work it out. There's a ton of information online about how to navigate all of the basic Jupyter and Anaconda setup, but I'm happy to help in any way I can. All right, the next thing that we need to talk about is the actual notebook files, the workshop, data camp, whatever you want to call it, the files that we're going to be working from. So here I am on my GitHub page. This is a photo of me from when I was a much younger man and established my GitHub online presence. We're going to be working from the STEMNetX_coding_camp repository. So I'm just going to double click on this or click on it once. It's going to take us into a little set of folders here. If you click on Asynchronous Workshop or Async Workshop, it's going to take you to a folder that has all of the notebook files that we're going to be using for this coding boot camp or workshop. And they're numbered. You'll see more of this information in just 1 minute. What we want to do right now is we're just going to download the first of these. So I'll click on this guy and I'm going to click this little download raw file button up here. And Chrome browser gives me a little notification that this thing has downloaded and it's done. The next thing that we need to do is we need to open this notebook file in Jupyter Notebook. So I'm going to go back to the browser tab that is my Jupyter Notebook, and I have to upload. This is kind of weird language because we're basically just going to tell Jupyter Notebook where to find this file that we just downloaded. I'm going to click on upload. I'll get a little file browser here. I will go to my downloads folder. Oh, look, I'm already there. And if I just scroll around until I find that STEMNetX, oh, there it is, STEMNetX 1.0 basics.ipynb. I'll open that guy. There it is. It's now in my Jupyter environment, and I can click on this thing, and it'll open. Huzzah, look at that. So again, if you can get to here, you're already doing pretty darn well for yourself. So at this point, we're kind of off and running. So we have 9 of these notebook files. Each one covers a different set of techniques or a different set of applications in the world of Python, and really applications in terms of data science or computational science or applications for quantitative sciences. The way you should be using these is watch the videos. There's going to be 1 video per workshop notebook file. In the videos, I'll walk you through these pretty quickly, and I will show you some examples. I'll do some live coding demos. It'll be fun. You'll watch me fail and then figure out what I did wrong to give you the sense that, okay, failure is an option, and it will be an event in your near future. We'll talk about how to solve problems and how to figure out what error messages are and things like that. Then, after you've watched the video, go back and actually work through the notebook file. So there's a lot of information in these notebook files. They've been lovingly written by yours truly. They have a lot more information than I'm going to say out loud, a lot more resources, links, and things like that I won't click on in the videos. There's a lot more instruction in the notebook files than what I'm going to say out loud on these video recordings. There are opportunities for you to test your knowledge. There are example problems, and there are also some homework problems at the ends of some of the notebook files. So without any further ado, let's get into it. Welcome. So this is the asynchronous, whoops, this is the wrong file. Oh my gosh, we are failing here. Hold on 1 second. Let me get rid of this guy. We'll delete that, and I want to permanently delete that. And I uploaded the wrong file. Let's see, where would it be? Async, here it is, async STEMNetX underscore 1.0 underscore basics.ipynb. And I will get that guy, and now I'm gonna open this thing. Sorry, I opened up the notebook file for the synchronous part of the workshop. Here we are with the asynchronous. So I told you I was gonna fail, and you were gonna see that live in the recording. It happened even before I started coding. All right, so here we are, welcome. Here's some info about me. My name's Mike McCracken. When we interact, you can just call me Mike. I'm a physics professor here at W&J. I've been here since the fall of 2008, so quite a long time, 15, 16 years, depending on how you count. Why am I leading this coding boot camp? So you'll get a sense, hopefully a better sense, as we go through the workshop. The computation is absolutely an indispensable tool in modern scientific research fields. In my field of particle physics, you can't do particle physics without doing large-scale data analysis. And pretty much any experiment that happened after the, I'm going to say, mid-1970s requires computers to crunch the enormous amounts of data that particle physics experiments spew out in, seconds of operating it. So the experiment I worked on, I think at this point we've generated something like 10 petabytes of data. That's a lot of bytes of data. You would not comb through that data by hand or in an Excel spreadsheet or something like that. More importantly, I absolutely love programming, and I love working with students to develop their programming skills, especially as applied to doing scientific research. So this is right in my wheelhouse. I love doing this kind of stuff. If you need to contact me, email's best. There's my work email right there. Okay, the workshop resources, you're seeing them right now. They're all available on my GitHub page. You can also take a look, if you want, at the textbook that the physics department at W&J has written for a course that we teach in computational sciences called Physics 250, Intro to Computation for the Physical Sciences. The materials for this workshop were developed from the textbook that we wrote. The textbook has a lot more information in it, but if you click through it, you'll see some of the same things. And by textbook, I really just mean more of these Jupyter Notebook files. So here's the agenda for this workshop. As I mentioned before, we're going to have 9 lessons. Each will have its own notebook file and video like you're consuming right now. A good plan of attack for you all would be to spend 2 days working on each lesson. So here's the list of lessons or modules, however you want to think of them. We have 1.0 all the way through 4.1. I've grouped the lessons into modules. So there's module 1, which comprises lessons 1.0 and 1.1. There's module 2, which comprises lessons 2.0, 2.1, and 2.2, and so on, just because the lessons in each module are kind of thematically linked. You should consume these in order, but you shouldn't feel like, oh my gosh, I need to understand the overarching concept behind module 2 before I move on to module 3. If you can glean the overarching idea, that's great. Not totally necessary. All right, for asynchronous workshoppers, here's a good approach. So a good plan for consuming these lessons is to watch the video for each lesson, pause to execute the cells in the Jupyter Notebook that you're working through. You'll see more about what that means in a moment. Then go back and read through the notebook in closer detail, work through some of the example problems. Number 3, execute or modify the code cells as instructed. So when you read through the notebook file in greater detail, you'll see that I'm giving you instructions about how to manipulate things. And 4 and 5, do it yourself. Try a couple of the warm-up problems and try a couple of the homework problems. The difference between, so you're not going to be handing in any homework in this workshop. That would be a class, and this is not really a class. The difference between warm-up problems and homework problems is that warm-up problems are more in line with the type of thing that we're doing in a notebook file. So a warm-up problem is something that you should definitely do or watch me work through before we move on to the stuff that comes after it in a notebook file. Homework problems are more like, okay, I'm done consuming this notebook file, I'm done consuming this lesson. I'm now going to flex my muscles on a kind of a longer term problem. So it's something that might take you 30 minutes, an hour over the span of 2 or 3 days. You might need to bang away at it for 15 minutes, realize you're hitting a wall and then think about it in the background for a couple hours before you come back to it. You'll see more about what I mean by that when we get to them. Okay, setup and background. Here's some more information about Python and installing Python. So we're going to be using the programming language Python for this data science bootcamp. I will let you read all of what I feel are good reasons for using Python. There are two that I'll highlight right now. One is that Python is free and open source, so you've gotten it free. You didn't even have to steal it like you do for some other software packages. Don't steal software packages. So Python is free. It's also open source, so you could download the source code for Python, modify it, and make your own version of Python if you wanted to, if you felt there was some way that you could improve it. You could also, more importantly, contribute to the open source community that develops and maintains Python. So this is a really cool software project that includes, probably hundreds of thousands of people from all around the world who are contributing to Python. The big benefit for us, you're probably not going to be doing that before the end of this workshop. The big benefit for you in this workshop is that because Python is open source and there's a huge community of Python developers and users, there's a ton of free and easily findable documentation online. If you bump into a problem using, installing, modifying Python, chances are good that tens of thousands of people have made that same mistake, bumped into that same problem, and probably at least 100 of them have written something about how to fix it online. So, it's very Googleable. The errors that you will encounter, the things that you want to do, you'll be able to Google those and find some great guidance. You also have me, of course, but the online community is absolutely fantastic for Python. All right, what is the goal of this workshop? What are we even doing here? I'll again let you read the finer points here, but the TLDR is we're going to investigate some of the foundational principles of computer programming, specifically those which are useful in the physical or quantitative sciences. So if you've taken a programming course in the past, if you've used Java or C++ or something like that, most computer programming courses that are taught in computer science departments are absolutely excellent, but they're oriented toward the types of things that computer scientists do in a standard undergraduate curriculum. This is things like maintaining databases, building web interfacing protocols, all kinds of stuff like that. In the physical sciences, our toolbox is a little bit more limited, but it's also specialized. The types of programming that we do is really for analysis of quantitative information, analysis of large data sets, and then graphing, fitting, things like that. Those are the skills that we're going to cover in this course. After you complete this workshop, you will not be a computer programmer. You'll be someone who has programmed a computer to solve science and mathematics problems. There's a lot that you won't know, but some of the things that you will know are not covered in a standard undergraduate computer science curriculum. So you'll have complementary knowledge there. Again, you can read all of the details here on your own time. Some quick terms. So we're going to be doing coding in this workshop. Coding is just a fancy or a cool way of saying computer programming, basically writing instructions that a computer will execute. So if you watch, one of those crime scene investigation shows where they have like a really cool hacker type person on it, that person coding just means they're writing computer programs. Data science is an umbrella term for the tools that we use in making decisions based on analysis of data. So it's a kind of a broad set of skills that we use to take quantitative data or even textual data or data in general, and then analyze that data so that we can make decisions based on it. We'll get into that in more detail later. Scientific computation is another umbrella term for the types of computer programming that we often use in scientific fields. So again, this is a difference from building web protocols or communication protocols. We're really talking about the quantitative skills, analysis tools that we apply in the sciences. Okay, so if you've never done any coding or computer programming before, it can be very intimidating. It can be very confusing. Like, what are we even doing here? The basic idea is that we are figuring out the syntax. We're learning a new language. That language is Python. It's the language that your computer speaks. It's one of many languages that your computer speaks. If you want your computer to do something, you have to speak to your computer in the language that it understands. Very similar to acquiring, a human language, second human language or something like that. Again, I'll let you read this in much more detail. All we are going to be doing in the first few lessons of this workshop is learning the syntax for giving instructions to the computer. That's what we mean by learning how to program a computer. The last few modules, or the last few lessons, we're going to be taking those communication syntaxes that we've learned and combining them together into applications. So what are all the wild and wonderful different things that we can do with those basic skills that we've learned so far? If you ever get frustrated or confused or lost and just like, what am I even doing? All of the problems that we're going to work on are problems that you would be able to state to another person if you were working with a classmate and you told them, hey, we need to generate a list of the first 100 prime numbers. Like, that's a very straightforward thing to understand if you know what a prime number is. Instructing a computer how to do it is another level, right? We have to learn the language first to tell a computer how to do that and how we want the computer to do that. So that's what we're going to be doing in this workshop, is learning that syntax. All right, Jupyter Notebooks. We're in a Jupyter Notebook file right now. So the whole idea with a Jupyter Notebook file is it's this really convenient container for both text, like we've been reading so far, and Python code, Python software, Python language. So in a Jupyter Notebook, this is a Jupyter Notebook, this browser tab, this thing that opened in the browser tab, we have markdown cells. Markdown cells are the ones that contain text. If I double click on one of these cells, you'll see the actual source code for the markdown. And then if I want to render this markdown, I get my cursor in that cell and press Shift and Enter at the same time. And you can see that cell renders as this beautifully formatted text. There are also code cells, which just contain Python code that gets executed. So when I render a markdown cell by pressing Shift and Enter, all it does is just renders the text. When I execute a code cell by pressing Shift and Enter, the computer is actually going to ask Python to run the code that I've put in that cell. And you'll see more about this as I scroll down. But the real takeaway from this little blurb is that if you want to execute a cell, be it markdown or code, you press Shift and Enter simultaneously. Okay, so I've already showed you how to download and open a notebook file. That's great. I'm doing great. Okay, get on with it, Mike. Okay, fine, let's do this. So let's start with some really basic syntax. This first lesson, it's going to seem like we are turning your computer into a really lousy, cheap $10 calculator. Because all we're going to do in this first lesson, most of what we're going to do in this first lesson is just investigating the mathematical syntax. How do we tell Python to do mathematical operations? Some of the ways of doing this, some of the syntax is really straightforward. So here's like if I wanted to add 2 plus 2 plus 2, there's the syntax for it. You'll notice that this cell is a different type of cell than the text or markdown cells that we had above. If I click on this cell, it tells me that it's a markdown cell. If I click on this 2 plus 2 plus 2 cell, it tells me that it's a code type cell. If I want to run this cell, I put my cursor in there and I hit Shift and Enter. So, oh my gosh, look at this, groundbreaking stuff. 2 plus 2 plus 2 is 6. Here's another cell. If I want to do multiplication, 3 times 2 is also 6. Here's another cell. It's a long string of calculations. I can execute this thing. Python does it really quickly. All right, let's guess about what we think this cell is going to do. So 2 caret 10, that little up arrow is called a caret, C-A-R-E-T. Usually means a number raised to another number. So 2 to the 10th power would be 1024. I totally did that in my head right now. I didn't look that up ahead of time. When I execute this cell, it turns out I do not get that. So here's our first little taste that Python mathematical syntax is not the same as the syntax we use in our TI 30 calculator or TI 82 graphing calculator, something fancy like that. The syntax is different. 2 caret 10 doesn't mean 2 to the power 10. It means something completely different that we're not going to get into. If I want to raise 2 to the power 10, the syntax that I would use is star star. So it's kind of like we're multiplying. It kind of makes some sense. I'm not multiplying 2 by 10. I'm multiplying 2 by itself 10 times. And of course, we get the right answer here, 1024. We can take the square root of things. I would raise, if I want the square root of 29, I would raise 29 to the 0.5 power. It's 5.38. I can do a list of calculations. So here's 29 square root, 29 to the 0.4 power, 29 to the 0.3 power, and so on. I can separate these by commas, and Python will do all of those things. It gives them to me in this kind of parenthetical list of values. We'll talk more about that in the future. We can also get into trouble. So just like on a calculator, if you enter a mathematical phrase that isn't valid, it'll tell you syntax error. Same type of thing happens in Python. So I'm going to uncomment this line. You'll notice that this code cell is kind of in this weird greenish color. If I remove that hashtag, that pound sign in front, I can do something like this. So 29.0 with that caret, which we know doesn't mean raised to the power of 0.5. When I execute this thing, I get what's called an error. So here's a little error message. So right out of the gates, the output cell is red. We know that means something wrong has happened, something's gone wrong. And it tells us, hey, you have a type error. This is an unsupported operand for these types, float and float. Basically, what Python is telling us is that it doesn't know how to use this caret symbol for two numbers like this. The actual details of this error is something that we're going to get into later. I just wanted to show you this is the type of thing that might happen if you incorrectly use syntax, or you use syntax that Python can't make sense out of. So you'll see some more information about this down here. This is our first example of what's called a runtime error. So a runtime error is code that just simply will not run. I tried to run this cell, I did Shift Enter in this cell, and Python just fails. It says, you know what? I don't know what the heck you're trying to tell me, so I'm just stopping the program right here. Here's some other examples of runtime errors, and I should mention this: the pound symbol in front of a line of code comments out that code. It means that Python is just going to ignore that entire line of code. So if I run this cell with that hashtag there, with that pound symbol there, it does nothing because it's ignoring the only line of code in that cell. If I remove that pound sign, it's going to try to run this cell, and we get a syntax error. It's telling us that we have incomplete input. It's giving us a little hint of where in the line that's happening. We opened a paren, and we're not closing with a paren. So Python doesn't know what to do there. What about this one? Let's comment this guy out. So 4.1, that's a number. It's 4 1/10. 4.1.6, no idea what to do with that, and Python doesn't either. So it throws a syntax error. What about this one? Okay, let's see what Python tells us here. Okay, 23 plus this big number plus A. Python says name error. The name A is not defined. We're trying to add up three things, and Python doesn't know what that third thing is, so it doesn't know what we want it to do. You will bump into runtime errors a whole lot over the next several days as you're learning to use the syntax. One of the nice things about Python is in some cases you're able to guess what the syntax for some new type of operation should be. Sometimes you'll get it wrong. Sometimes you'll just hit the wrong key when you're typing in, your code. There are all types of things that can go wrong. The error messaging in Python is actually pretty good. So it's pointing you right to the line where there is a problem. As our programs get longer and more sophisticated, you'll get better examples of that. All right, here's another operator that I want you to check out because we'll be using it a lot. This is % symbol is what we call the modular division operator. Basically what it does is it divides two numbers and gives us the remainder. So 12% 5 means, hey, divide 12 by 5 and tell us the integer remainder, or tell us the remainder of that division operation. 12 divided by 5, so let me see if I can do this. 5 goes into 12 twice in its entirety. So 2 times 5 is 10. I don't know why there are balloons popping up right now, but there we are. So it goes into 12 twice with a remainder of 2. You would have 2 left over, and that's what we're being told here. So 20% 5, what's the remainder when we divide 20 by 5? Well, it should be 0. That checks out. What's the remainder when we divide 345,702, 2835, 203 by 5? I don't know, and that actually sounds like it would take me a long time to figure that out. Actually, I should know. Should it be 3? Should it be 3? Let's see. Yeah, it is 3. Okay, because a number divisible by 5 would either end in a 5 or a 0, so we have 3 left over. So that wasn't too difficult. Here's one that would be difficult. Let's divide that by 7. Okay, so 5. I could not have guessed that one. But right there, you're getting an example of the operability here. So there's some simple mathematical calculations we can do in these cells. I can modify these cells. If I want to make this number longer, I'll just mash the keys right here. That's a really big number, and Python was able to figure out this modular division problem very quickly. Pretty exciting. We're going to use that modular division operator quite a bit in the future. It turns out to be really useful for applications in the sciences. All right, the next thing to cover is what we call variables. If you've ever programmed a calculator before, you're able to store some information in memory. That's the same type of thing that's happening here. For really long calculations, we often want Python or our computer to keep certain values in mind so that we can do calculations, computations with those things later. The basic way to do that is to set up what we call variables. So here's an example of a line of code that takes a value. This is negative 2.0 times 10 to the minus 9 power. So it's kind of like scientific notation-y. And it stores that value in a variable name. I'm telling the computer, hey, set up this thing that we're going to call A and store this value, negative 2 times 10 to the minus 9, in that variable name so that we can then access that information later on. So if I run this cell, it looks like nothing happens. We do get an output number, so Python is telling us something happened. But then later on, I can access that information that's stored in the variable name. So here I'm going to use a print function. I'm going to print out A. When I do that, I get minus 2e to the minus 0.9, which is computer speak for negative 2 times 10 to the minus 9. It's scientific notation. This is a really basic idea. You're basically programming the computer to store this value in memory. Doesn't seem that sophisticated. It actually is very important because using that technique, we can now set up more complicated calculations. So here's an example, very basic example. I'm going to do an ideal gas law calculation. So if you've ever heard of P times V equals nRT, the ideal gas law, that's exactly what we're going to use here. I'm going to set up some variables. The pressure, it's 101,300 newtons per square meter or pascals. The volume is 1.12 liters. I'm doing this kind of almost in SI units, I think. Or wait, I guess that would be 1.12 cubic meters. Yeah, that sounds right. N is the number of moles, 26 moles, and R is the ideal gas constant. When I execute this cell, Python is going to do each one of the lines in this cell in sequence. So first it's going to store 101,300 in the variable pressure. It's going to store 1.12 in the variable volume. It's going to store this in the variable N. It's going to store this in the variable R. Then it's going to do a calculation of pressure times volume divided by N divided by R and store that value in a variable called temperature. Then it's just going to print out this nicely formatted, the temperature of our gas is the value of the temperature and then Kelvin. So I did do this in SI units, let's hope. Hey, there we go. The temperature of our gas is 523.5 blah, blah, blah Kelvin. So this idea of storing information on the computer using variable declarations, really useful. I should mention, you probably know this already from what I did with A, the A variable above. Once I store that information in a variable, it exists for the rest of this notebook. I can change that value if I want. I can also recall and use it. So if I go down to this cell below, let's say I want to change the value of the pressure. I increase the pressure of the gas to 180,000 newtons per meter squared. I can redo my calculation and I get a new value. And the reason I can redo this calculation is because the volume, number of moles, and ideal gas constant values are still stored in the computer. I'm just reusing the values that were stored from before. Pretty cool. Again, seems very basic, but this is kind of the backbone of doing more complicated calculations, is storing information in the computer and then doing computation with those variable names. So I don't have to, think about how you would do this if you couldn't program a computer or a calculator. Every time you changed one of the parameters of that ideal gas, you would have to retype in the values to your calculator and then hit enter, redo the calculation every single time. If I vary, let's just increase this to 189,000 pascals, I can redo that calculation on the fly. And then what if you tell me, no, it was actually 190,000, I can redo that calculation on the fly. All right, here's some other shenanigans, converting to Fahrenheit temperatures, so you can check that out at your leisure. All right, so variable declaration, absolutely core skill. We'll use it pretty much in every code cell from now on. You'll see how that goes. Maybe not every code cell. We'll use it a lot. Next, we want to talk about functions. So just like in calc or pre-calc, we deal a lot with functions. Functions are these kind of operations that act on quantities, and they give us some output quantity. If you think about a one-dimensional function, maybe a linear function, y equals mx plus b, we call x the independent variable because it doesn't depend on anything, and we call y the dependent variable. That's a function for a line because you put in a value for x and you get out a value for y. We can define functions in Python, and here's a syntax for doing that. So I'm going to def, which is a keyword. Whoops, what happened there? Oh goodness. Thanks, Mac. I'm going to use the def keyword, which basically just tells Python, hey, get ready, we're about to define a function. I'm going to define a function called, oh my goodness, why is Mac doing that? My function is going to be called ideal gas temp, and it's going to take in two independent variables. So if I want to do a calculation with this function, I'm going to supply a press variable. It's just a name I give to it. It's short for pressure. And a vol variable. That's just a shorthand for volume. It's going to assume a certain number of moles. It's then going to multiply pressure times volume to give me some num. I'm going to store the value of pressure times volume in the variable number. I'm then, oh no, I guess this was num is short for numerator. And then I'm going to calculate the denominator, which is just the number of moles times the ideal gas constant, 8.31. Then I'm going to divide the numerator by the denominator. And the return keyword is the keyword in Python that tells, or the keyword that tells Python, hey, here's the thing that this function should output. You don't always need a return in a function definition, but for our purposes, most of what we'll do, we will be using return keywords. So again, we're in this cell defining a function, telling Python what are the input variables for that function, or the input values for the function. These three lines of code are kind of like the meat of this calculation. They're doing the calculations. And then the last, or the meat of this function, they're doing the calculations. And then the last line here basically just tells Python, okay, what should this function output? When I run this cell, we're going to get an output number. So Python did something. We don't get any output yet. The reason is we have to actually apply this function to something. So here it is. I'm going to use this ideal gas temp function. I'm going to supply two input values. I'm going to supply a pressure of 101,300 newtons per meter squared and a volume of 1.12 cubic meters. And when I execute this thing, the function returns the temperature. So it did the calculation internal to the function, and then it just spits out the temperature. I can then use this function again as many times as I want. I can input new values for pressure and volume, and I just use this function over and over again. The utility of functions in a programming language is a lot of what we're going to be doing in the demos that we'll do later in this workshop and in scientific computation is applying the same calculation over and over and over again to a whole bunch of input data. That sounds like a great use case for a function. So you wouldn't type out PV equals nRT over and over and over again every time you wanted to do an ideal gas calculation. You would program that calculation as a function and then just apply that function to new data as they come in or as you read them from a file or something like that. So just to give you a taste of what I'm talking about here, I'm going to show you a loop structure, and then in the next lesson, or maybe the lesson after that, it's probably the next lesson, we'll get into loops in earnest. A loop in the context of computer programming is a way of automating some repetitious task. So, well, let me give you an example right here. So the loop structure that we're going to study today is called a for loop. We'll get into much more detail in the next lesson. A for loop basically executes some computation for a fixed number of times. That's why we call it a for loop. Here's a really straightforward for loop syntax. So you can ignore the print statement. It's going to print out, let's compute the square roots of the first 10 non-negative integers. Then we have the for loop here. So the syntax is for is a keyword, I in this list of values. So what this for loop opening statement is going to do is it's going to set the value of this variable I. We call this variable an iterator because every time we iterate through the loop, its value is going to change. It's going to set the value of I the first time through the loop to be equal to the first value in this list. So the first time the loop executes, I will be equal to 0. The next time the loop executes, I will be equal to 1. The next time the loop executes, I will be equal to 2. Next time the loop executes, I will be equal to 3, and so on. Every time through this loop, or for each value of I, all of the code that's indented below that for loop will be executed as part of the loop. So every time through this loop, Python is going to print out the value of I, and then the value of I raised to the 0.5 power, just the square root. And then when the loop is done, we have a line of unindented code. That's how we know that we're exiting the loop. It's going to print out, we are now done. Let's see if this works. So I did a shift enter. Let's check these. Let's spot check these. So the square root of 0 is 0. The square root of 1 is 1. Square root of 2, 1.414. I remember that value. Square root of 3, yeah, it's probably 1.73. Square root of 4 is 2, great. If we go all the way up to 9, square root of 9 is 3. So computing square roots of a number of integers is really boring. It's really repetitive. So we programmed a computer to do it for us. You'll notice that that happens so quickly. Let me execute this again. It's like in the blink of an eye. If I were to try to compute the square root of the first, I don't know, let's do 1,000. Let's do 10,000 because that's good. So I'm going to do this. Range 10,000. I'll even do 10,001. Okay, so we've just increased the number of computations we're going to do by 1,000, or by a factor of 1,000. We did 10 before, now we're going to do 10,000, so 10,000 times more. When I run this cell, it happens, again, instantaneously. And you can see that this is a really, really powerful way of doing a task that would otherwise be really repetitive and boring. We get all the way down to here. The square root of 10,000 is 100. We will talk much more about the syntax of these for loops in the next lesson. For right now, I just want to show you why for loops or why functions are so useful. I'll let you read this one at your leisure. Maybe we can do, yeah, I'll let you read the others at your leisure. So what we could do is let's modify this cell to do this with a function. So let's do this. I'm going to define a function that I will just call square root, and it's going to take in a number. So I'm defining a new function. And what's going to happen is I'm just going to return the value of n to the 0.5 power. Now this seems really weird because this is already a very simple thing to code up, but I'm just going to show you how I can use this function, this square root function that I just coded, inside of this loop in order to apply it over and over and over again. So I run this guy, and I'm now applying this square root function that I coded up, to the first 10,000 non-negative integers. For a square root, that's not very impressive because, like I said, square root is a pretty straightforward calculation to do. If I wanted to make this much more difficult, let's say I had some much more complicated function, so n to the 0.25 power minus, what should we do? N times n to the, what do we want to do? N times n to the 0.1 power. I don't know what that'll give us. Let's just try it. And I have to fix that syntax there. Okay, so now our function is a lot more complicated, and I'm going to rename this complicated function. Okay, and now I just want to apply complicated function to my value of I. Oops, I got to use I in there every time through the loop. Yeah, so you see that I made a goof because the previous time that I executed that, I didn't apply my square root function to I. I was applying it to n, and that didn't change. So that was a goof. I didn't catch that earlier. You probably did at home. I mean, I did that on purpose so that you would have a teachable moment. When I now execute this, you can see that this function is applied to all of these 10,000 values very, very quickly. And we get some weird quantities. This thing has some zeros in it. Yeah, it's a weird function. Starts out positive, goes negative. I guess it starts positive and then goes negative. Might be interesting, might not. This is a it's a complicated function. It's still a very, very simple type of calculation relative to the things that we're going to be doing by the end of these lessons. So if you can internalize this idea of define a function and then apply it to a bunch of values in a loop, you're going to be in great shape. All right, so I will let you read this little section on numerical integration. Some of you have probably taken a calculus class. That's awesome. One of the things that you do in calculus is you approximate integrals by doing Riemann sums or by summing infinite series, doing partial sums of otherwise infinite series. A loop is a really great application of that. We'll come back to this in the next lesson. For now, let's do some homework. So let's just code up one of these. So the first two are pretty easy. So actually, we can do the first one in a couple different ways. What do we get if we divide 201 by 7 6 times? So the dumb way to do this is just to do 201 divided by 6, divided by 6, divided by 7, 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 divided by 7. Is that 6? Yeah, that's 6. Okay, I can run this now. Not very exciting. That would be the calculatory kind of way to do this. We can also do this with a loop. So let me do something like this. So let's do it in the following way. So I will call a start number. I'm going to make it 201. And then I'm going to do for I in range 6, which basically means do something 6 times. I'm going to, check this out. I'm going to divide start by 7, and then I'm going to store that value back in the start variable. So this syntax is pretty cheeky. What it's doing is it's dividing start by 7 and then taking the outcome of that calculation and storing it back in the start variable. So it's like doing the calculation, then overwriting the value of start with the new value that we get from dividing start by 7. And then at the end of this calculation, let's do print start. Hey, we get the same value, and it happened pretty darn quickly. I can also, let's do this. So let's just, I'll print out start at the beginning of this process. And then every time we step through this loop, I will print out start again, and we'll get some more information just to see how this kind of happens. And we probably then don't need this at the end. Great. So we start with 201, divide by 7 once, we get 28.7, divide by 7 again, we get 4.1, and so on and so forth, all the way down to our final value. All right, number 2, how would we check this? So is 438,095,307.53 divisible by 233? One way that you could do this is to just do that division. So I could do something like, I'm not going to type out this number. Let me just copy this guy. There are a couple different ways to do this with just basic mathematical syntax. I could do this, and because I don't get a whole integer, I know that this number is not divisible by 233. I could also check this with the modular division operator. So if I divide this big number by 233, and I get any number other than 0 as a remainder, then I know that the big number is not divisible by 233. Let me get 32. Okay, great. All right, so here are 2 more homework problems. These will probably be, let's not do these right now. Let's talk about these in more detail, or you'll see how these are going to be more approachable after we talk about the looping syntax in more detail in the next lesson. So for right now, I will leave you there. This is just the tip of the iceberg in terms of becoming comfortable with Python syntax. All of the things that I covered in this lesson, we're just going to reinforce more and more and more over the next few lessons. So if you're feeling overwhelmed, don't be. If you feel like there's some secret that you missed in this lesson, don't feel that way. We'll be returning to all of these ideas in the next few lessons. See you soon. Let me remember how to stop recording. There it is.